In this exercise, we would like to convert the following arbitrary given numbers to binary, decimal, and hexadecimal. We also would like to investigate the conversion potential in both the signed and the unsigned representations. Looking at the first table, the left-hand section represents the natural numbers, and the right-hand side represents the signed numbers. Now, the difference between the natural and the unsigned is that the natural numbers start from 1, whereas the unsigned includes 0. In our case, this is the same, so whenever we mention natural representation, it's the same as unsigned. The right-hand section of the table represents the signed numbers, so this is the signed part. One important note is that the restriction given in this exercise is that all conversions should be based on 8 bits. Eight bits means that we have 256 combinations. This means in unsigned or natural coding, if we include 0 as one of the possibilities, then the maximum number will be 255. If I assume this is my number, then it would vary between 0 and 255. However, in signed coding, my number will vary between 2 to the power 8 minus 1 minus 1 down to 2 to the power 8 minus 1. And here 8 is the number of bits used. So this means in this case x would vary between 127 to a negative 128. So the counting in the natural coding would be something like this, starting from a decimal of 0. The binary for an 8-bit representation would be 8 zeros, and the hexadecimal is 00. If we keep counting all the way, then we will end up with the last number for an 8-bit, which is 255. This is equivalent to However, for signed coding, this will be different. So in signed coding, we start from 0 all the way to the maximum allowed number. In our case is 127. And as we add further, we will actually jump to the negative 128. And as we keep adding, we are actually increasing. We are actually increasing from the negative 128 all the way to a negative 1, which is represented as 8 ones for an 8-bit representation, or FF for a hexadecimal representation. If you notice as well that all the negative numbers in signed representations, they start with 1 on the left hand side. Remember, conversion between binary, decimal, decimal to hexadecimal were explained in more details in exercise 1 and 2. Given a binary number with 8 bits, we can write the decimal number as equal to the sum of binary numbers multiplied by their powers of 2. So to convert from whether binary to decimal and vice versa, it's handy to write the below relationship, where a could be either 0 or 1. 2 to the power 7 is in fact 128. Is 128 in a natural coding, and it is a negative 128 if it's a signed coding. And 2 to the power 4 is 16, 2 to the power 3 is 8, four, 2, and 1. Let's take the first decimal of 0. The number 0 in decimal, whether we are using natural coding or signed coding, this will also lead to 8 zeros for an 8-bit representation. And it's 00 for hexadecimal representation. If we take the second decimal of 100, the 100 is in fact 64 added with 32 added with another 4. If we replace ones in those places, we will end up with the following binary. And if you go back to our exercises 1 and 2, you need to look at 4 bits at a time in order to convert this to hexadecimal. The first 4 bits, in fact, they represent a number 4, and the 0110 represent a hex of 6. Since the number 100 is below the 127 and is still within the signed coding range, then that would be the same numbers for the signed representation. If we take now the negative 50, there is more than one way to represent this in its signed coding representation. So the first method, perhaps you could take the absolute value of this. So if you have a minus 50, if you take the absolute value, this would be 50. The binary representation of 50 is simply 132 and 116. That will leave us to a 48 and one of the two. So we end up with 0, 0, 1, 1, 0, 0, 1 for the 2, and 0. Now what do we do normally is we simply suppose this is A, then A bar would be 1, 1, 0, 0, 1, 1, 0, 1. Now A bar plus 1, that should give us the negative 50. It's simply we add 1 as 0, 1, 1, 1, 0, 0, 1, 1. So this actually is the representation of minus 50. That's one way to do it. So we can write the representation of a negative 50 as 1, 1, 0, 0, 1, 1, 1, 0. In order to find the hexadecimal of this signed representation, simply look at the first 4 bits, and the 110 in fact is the number 14, so this is letter E. and the 0011 in fact is number 12, so that's going to be C. Since the negative 50 can be only represented in assigned coding, then for the natural representation this is not applicable. If we look at the fourth number, this is given in hexadecimal. In decimal, this is equals to 1 times 16 to the power 1 plus 0 times 16 to the power 0. This leads to number 16 in decimal, so this is 16. To convert the hexadecimal to binary, straightforward. Look at the first hexadecimal digit, it's 0, so this is 4 zeros here, and number 1 is a simple 1, so that would be 1 0 0 0. Since number 16 is common to both the natural and the signed coding, then we can write the same number for the signed representation as well. Let's take now the negative 34. If we do the absolute, the number 34 is actually 32 and another 2. So the binary representation is 0, 0. This is 132, 016, 08, 04, 12, and 01s. Then A bar is 1, 0. Simply flip, put the 0 as 1 and the 1 as 0. So the A bar plus 1 is simply adding 1 to this and in fact this is the negative 34. If you're not sure how to do this, it's very simple. Let's take A bar again. It's 1011, 1011. That's the A bar. We add 1, one and 1 is 0, add 1, and that's the A bar plus 1, which is the negative or the opposite of the initial number. In this case, the initial number was 34, now our number becomes negative 34. The negative 34 now can be represented in the signed coding as 11, 01, 111, 0. The first half byte is the letter E. This is number 14. And the second one is letter D. And D here is the number 13. You can refer back to exercise 1 and 2 for more details about the hexadecimal to binary conversion and vice versa. Now, since the negative 34 can be only represented in assigned coding, then the natural representation is not applicable. If you're not interested in this method to find the opposite of the number, you can still use the original relation between decimal and binary by taking into consideration that the first bit represents a negative number. For example, a negative 34 is in fact negative 128 plus a 64 plus a 16 plus 8 plus 4 plus 2 plus 0. This equals to, this is minus 34. Simply, in this case, you have to put 1 at A7, 1 at A6, and 0 at 32, 1 at 16, and 1 at 8, 1 at 4, 1 at 2, and 0 at the A0. So in this case, you end up with the same result. Let's take the plus 130. Since this number exceeds the maximum allowed number in the signed coding, then we won't be able to represent this in a signed coding using an 8-bit representation. So we won't be able to represent the 130 because simply 130 exceeds the maximum allowed number for a signed coding of 8 bits. We need more than 8 bits in order to represent the 130 in a signed coding. However, 130 is well within the natural coding range, so we can normally convert the 130 to binary and hexadecimal accordingly. 130 is simply 128, one of the 128, and simply 1, 2. 128 plus 2 is 130. So we can write the 130 as 1, 0, 0, 0, 0, 0, 1, 0. As a hexadecimal, the first half a byte is the number 2. And the 0, 0, 0, 1 is simply 8. Let's take the negative one. The negative one is not within the natural coding range, so in this case we cannot represent a negative one in the natural coding. So this is not applicable. Whereas the negative one is simply 8 ones. If you're not convinced, take the first one as a negative 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and the answer here is minus 1. So you need ones on all of the bits. Alternatively, we can find the equivalence of a negative one by first taking 1. This is equivalent to 1, 0, 0 in 8-bit representation. Then we take 2's complements. So a bar, we need to find a bar plus 1, but a bar on its own is as such, and then a bar plus 1 in fact is 8 ones. So the negative one is simply 8 ones. In hexadecimal, this is FF, because the first 4 bits represent an F and the second 4 bits represent another F. Similarly, for a negative 3 number, this is outside the natural coding representation, so this is not applicable. Whereas for the signed coding representation, a negative 3 can be found easily by taking first number 3, it can be represented as 11000000, assuming this is A bar would be 0011. Then the opposite of 3, which is negative 3, is A bar plus 1, which is 1011. We simply added 1 to A bar. So a negative 3 is equivalent to 11111101. In hexadecimal, this is equivalent to the first 4 bits is a letter D, and the 4 ones is a letter F. Now, the following number is given as assigned coding in hexadecimal, which is 41. This can be converted to binary in a straightforward way. The number 1 here is simply 100010. Number 4 is simply 0010. Let's find out what is this binary's equivalent in decimal. This is 0100. You will notice that this is a 64 and this is a 1 by following the below representation. This is actually a 65 in decimal. Now, since 65 is a positive number and within the natural coding as well, we can simply represent this in a natural coding as is. So that will be 41, and this is going to be 10000010. This is 65. Let's take the final number. We are also given a signed number as E0. The binary representation of E0 is straightforward. The first digit in hexadecimal 0 can be represented by 4 zeros in binary, and the letter E is 14. This is equivalent to 0111. But what's decimal equivalence of this? So the 1110 is actually, there's 128 in it, and because we have 1 here and we have signed, so that becomes minus 28 plus 64 plus 32, and the answer is negative 32. Now, since a negative 32 does not belong to the natural coding range, then this cannot be represented in a natural coding representation. So that will be not applicable here. In table number 2, we would like to repeat the same procedure in order to write the representations of those numbers as assigned binary and hexadecimal. The main difference, though, is that first we need to find this representation in an 8-bit signed coding, then we need to do the conversion to a 16-bit signed coding. So this table is made up of 2 sections. The left-hand side is an 8-bit representation, and the right-hand side is a 16-bit representation. Let's take the negative 110. If we take the absolute value of this number as 110, the binary equivalence would be, so we don't have 128 in it, 0. We have 164. We can have another 132, and we can have a 016, we can have 18, and 14, 12, and 0. So that would be 64 plus 32 plus 8 plus 4 plus 2. A bar, in this case, is the opposite. So 0 becomes 1 and 1 becomes 0. Now A bar plus 1, adding 1 to this will lead to 0, carry 1, that was going to be 1, 0, 0, 1, 0, 0, 1. So for an 8-bit representation of a negative 110, this can be written as 0, 1, 0, 0, 1, 0, 0, 1. And the hexadecimal representation, if we look at the first 4 bits to the right, this is 2, and this is like 9. Now, since this is a negative number, if you would like to expand this from 8 bits up to 16 bits, then we have to write it as follows. So first we copy the 8 bits, and since the last digit is 1, we can extend this number by 1s until we reach the 16 bits. So we add another 8 bits of 1s. This is how we expand the number of bits based on the sign of the number given. And if you would like to express this now in hexadecimal, it would be the same as the 92, but with another F and another F on the left hand side. So that would be 29 FF. If we take a negative 79, let's assume that we have the absolute of minus 79. This is a 0, and we have 64 in it, 032, 016. We have 18, 14, 12, and 1. So A bar is the opposite, and the opposite of 79, which is a negative 79, is simply A bar plus 1. This is 1, 0, 0, 0, 1, 1, 0, 1. So 1, 0, 0, 0, 1, 1, 0, 1. Now the hexadecimal equivalence of this, the first 4 bits is 1, and 1101 is 11. This is B. Again, since this is a negative number, negative 79, ending with 1 at the far left side, then we can continue with 1s in order to expand the representation from 8 to 16 bits. So first we copy the first 8 bits, and then we continue with 1s, and the hexadecimal representation for this would be FFB1. Now we know, we proved this before, that minus 1 is simply all 1s. Expanding this to 16 bits would be 16 1s. Number 6 is a positive number. It can be represented in binary as 4 plus 2. So that's gonna be 0, 1, 1, all zeros. And hexadecimal, this is the first 4 bits is 6 and 0. If you want to expand this in a 16-bit representation, let's first copy the first 8 bits as 0, 1, 1, all zeros. Expanding this to 16-bit will simply can be written as a continuation of zeros, because this is a positive number. And the hexadecimal representation is 0, 0, 0, 6. Finally, the 99 can be represented in binary. So the 99 can be represented by the addition of 64 and a 32. This will give us 96. And we need another 3, so we need 1, 2, and 1 of the 1s. So the binary representation of 99 can be written as 1, 1, and zeros, 132, 164, and 0, 128. And the hexadecimal representation of this, the first 4 bits is a digit 3, and the other 4 is 6. To represent this in 16 bits, let's first copy the first 8 bits, 1, 1, 0, 0, then we have a 0, 1, 1, 0. And since 0 is the last digit on the far left, we just continue with zeros. And the hex representation will be 0, 0, and then we just simply copy the 63.